Today we are going to start kinetic theory of waves in plasmas. Well, today we will discuss what is the need for kinetic equation or VIasov equation. We will develop a physical picture of Landau damping, which is a very important effect of kinetic description of plasmas. We will define a distribution function, deduce VIasov equation, then solve this equation by the process of linearization in the presence of a plasma wave perturbation. We will employ the technique of Fourier Laplace transform to solve this coupled set of VIasov equation and Poisson equation, and we will discuss Landau prescription for analytic continuation of the function. Well, our presentation today will be based on these books, one by Stix, another one by Kral and Trivelpies, and a book by F.F. Chen. Let me begin with the need for kinetic description of waves and instabilities in plasmas. As I mentioned before, that plasmas have electrons and ions, and both these species have random velocities. Especially the electrons have very large thermal velocities, and often the average velocities or drift velocities are less than the thermal velocities often. And the main consequence of these thermal velocities or random velocities is that if there is a particle moving with velocity v, and if it sees a wave, electrostatic or electromagnetic, suppose this particle sees an electrostatic wave of potential A is equal to A e to the power minus I omega t minus k dot r. Suppose this is the potential of a wave as seen by a particle moving with velocity v. Then if there were no field, then the position of the particle in terms of time will be given by original position, some position at time t equal to 0 plus v into t. So, if I substitute this expression for r in here, my phi appears to be a exponential minus I omega t minus k dot v into t minus k dot r 0. The thing is that the effective frequency of the wave is not omega, but omega minus k dot v, because this is the coefficient of t here. So, the velocity, the frequency of the wave as seen by a moving electron is omega dash, which is equal to omega minus k dot v. This is a very important effect, that different particles in a plasma will see the wave of different frequency. And as we learnt in the case of true stream instability, that the response of a group of electrons, which we call beam electrons, the drift velocity that you calculate due to the plasma wave, this scales as 1 upon omega minus k dot v or k dot v 0 that we call as, this is the kind of thing we got. Now, the thing is that whenever this quantity becomes 0, the response is very huge. So, some particles, for some particles this quantity can become 0, those particles are called resonant particles. For other particles this may not be 0, it will be different. So, whenever you want to examine the resonant wave particle interaction, and that those particles play a very dominant role in energy transfer or growth or damping of the waves, you must go to kinetic description. That is one important thing. Second thing, in case of magnetized plasmas, what happens that suppose I have a magnetic field acting along z axis. And we know that the electrons gyrate about the field lines, and their x component of velocity, for instance, is related to, is in terms of time, can be written as rho sine omega c t, where rho is called the Larmor radius and omega c is the cyclotron frequency. This is the velocity of, sorry, I am talking of x. X coordinate of electron can be written like this, plus some constant x0. Now the issue is, or I will call this xg actually, guiding center. So the electron will gyrate about the lines of force, and x coordinate of the electron suppose behaves like this. And suppose I am launching a wave with k vector perpendicular to this is my k vector of a wave. So if I have a potential phi which goes as a e to the power minus I omega t minus k x, for instance, what I should do, this x I should substitute from here. So there is a time dependence contained in this term. So the frequency of the wave seen by the particle which is gyrating is not omega, it will be omega minus something else coming from here. And when you substitute this, what you get is the following, that phi as seen by the moving electron would be a e to the power minus I omega t minus k rho sine omega c t minus k x 0. Now there is a Bessel function identity that says that exponential of I alpha sin theta is identically equal to summation over n going from minus infinity to plus infinity integer values j n of alpha exponential of I n theta. So what you can do, exponential I k rho sin omega c t can be expanded in this way, and phi can be written as a summation over n j n of k rho exponential minus I omega t minus n omega c into t minus k x 0. So the effective frequency of the wave is no longer omega, but it is omega prime, which is equal to omega minus n omega c. That is very important. And another important aspect is that the Bessel function argument has k rho. So different effective frequency components will depend on how much is the Larmor radius, and how much is Larmor radius? It depends on the electron velocity perpendicular to magnetic field upon cyclotron frequency. So it is a function of velocity, and since different electrons in a plasma move with different random velocities, rho is different for different particles, and consequently their response will be, the effective field seen by those different electrons will be different. That is very important. So these two aspects, that finite Larmor radius effects are important and they are different for different electrons, and second, the effective frequency of the wave is Doppler shifted, and that gives rise to resonant interaction of some particles with waves. From these two aspects, it is necessary that we go over to kinetic equation or velocity theory of waves. Well, before I delve into details of kinetic theory, I would like to mention to you the phenomenon of Landau damping that so strikingly is described in plasma physics theory as a manifestation of kinetic effects. So let me talk about the physical mechanism or physical picture of Landau damping. we have already learnt the true stream instability in which there was no collision, still beam energy was transferred to the plasma wave. Now, here we are having a system of electrons, many electrons, and usually the distribution function in a plasma, if I plot one dimensional distribution function, means number of electrons, suppose moving with velocity Vz and Vz plus d per unit range in Vz. So, f I will consider to be one dimensional distribution function, which means the number of electrons have, I would say that f dVz is the number of electrons having their velocities in the range Vz and Vz plus dVz per unit volume, space volume, per unit space volume. Electron velocity in general is a function of electron velocities are in general 3 components, Vx, Vy, Vz, but forget that. Suppose I am counting only the Vz of the particle irrespective of how much Vx, Vy they have. If I consider particles in a unit volume and measure their z component velocity between Vz and Vz plus dVz, then their number is found to be proportional to dVz, and this quantity f is then known as particles per unit velocity range. And if you plot, usually this is going like this. So, particles with small velocities are larger in number and large velocities are smaller in number. Usually this is the kind of behavior you observe. Now, consider a wave travelling in the system in the same direction, z direction, with vector k, kz, and the frequency of the wave is say omega. So, the phase velocity of the wave would be somewhere here, omega by kz is somewhere here. Now, these particles which are in the vicinity of this omega by kz, they have a Vz equal to omega by kz, which is the phase velocity of the wave. These particles will be moving with the same velocity as the velocity of the wave, and consequently the frequency of them, of the wave seen by them, will be 0. However, omega by kz is just a point, but it is important that you consider particles in certain range here, slightly slower than omega by kz and slightly faster. What will happen? So, if I consider these particles are called resonant particles or quasi resonant particles. Now, let us see what will happen. How will these electrons which are moving slightly faster than the wave, how will they exchange energy with the wave? How will they bunch in retarding or accelerating phases, and how the slow moving particles will bunch? So, in what way they are going to have net energy gain from the wave or net energy transfer to the wave? Let us examine this issue. So, if I go to consider especially a wave of say electric field, say let me write electric field E is equal to say z cap, A is the amplitude, A cos omega t minus k z. Suppose I consider a longitudinal wave propagating in the z direction with frequency omega in the laboratory frame, and phase velocity of the wave is Vp, which is equal to omega by k. Now, please, in order to understand the interaction of resonant particles with this wave, we go to a frame of reference. So, go to a frame moving with velocity omega by k z cap or Vp z cap. In this frame, if I carry on the Galilean transformation, if I treat the particle to be moving with non-relativistic velocity, wave also to be moving with non-relativistic velocity, I can carry out the transformation to a moving frame, and then the electric field will be written as, let me write this, E would be written as z cap A cos k z prime. Z prime is the coordinate, z coordinate in the moving frame. Now, the force on the electron of charge minus E would be minus E into E z, which is minus E A cos k z prime. It is independent of time, but now let us examine how it looks. So, the force experienced by an electron in a moving frame will be so much. It starts from here, goes here, comes here. Now, the force F z as a function of z prime I am plotting, I am getting this region where force is positive. In the positive z direction, so I will call this as the accelerating zone. This force is negative, so I will call this region as the retarding zone, because this tries to retard the particles, slow down the particles. So, now consider there are two streams of particles, one moving with Vp, Vz greater than Vp. I will call group 1 particles. In the moving frame, their velocity will be positive, because in the left frame their velocity was more than the velocity of the wave. So, these electrons will appear like going this way. Like this. Now, what will happen? When the wave is having a positive F force on these electrons, they will move more quickly from here to here. So, they will move rather quickly from here to here, very quickly they will go there. Whereas the electrons here, they see a retarding force, so they will slow down and they will spend more time here than crossing this boundary between retarding and accelerating zone. Consequently, there will be net bunching of electrons in the retarding zones. So, in this case there is a net bunching of electrons in the retarding zones. Let me repeat the argument. Initially, when the wave is not there, all the electrons are moving with a velocity Vz minus Vp in the forward direction, which is nearly 0, but it is still finite. So, when the wave is there, then the electrons which are in the accelerating zones, their velocity will be enhanced, because the force is accelerating in the forward direction. So, they will quickly move from the accelerating zone to retarding zone. Whereas the electrons which are in the retarding zone, they will be slowed down, because the force is in the negative direction, the force is in this direction, the force is positive here, negative here. So, these electrons will be slowed down, they will spend more time here, plus some additional electrons have arrived from here. So, there is a net bunching of electrons in the retarding zones. And as we see, the retarding zones are the areas where the wave retards the particles, it takes away energy from the particles. So, there is a net transfer of energy from particles to waves. So, these particles, these electrons give net energy to the wave. Now, if you consider second bunch of particles, second group of electrons, let me just mention here group 2 electrons for which Vz is less than Vp, these electrons will appear moving in the backward direction, and consequently the ones in the retarding zones will be quickly moving out to the accelerating zone, and the ones which are in the accelerating zones, they will be slowed down. So, there is a net bunching in the accelerating zone, net bunching in the accelerating zones, and these electrons then gain energy from the wave. So, these electrons gain energy from the wave, energy. So, there are two distinct behaviors of electrons which are moving faster and slower. If the number of fast moving electrons were larger, then there is a net energy transfer from particles to wave and the wave will grow. On the other hand, if the number of slower electrons is larger, then there is a net gain of energy by the electrons from the wave and the wave will damp. So, it depends on which group number is larger, and this will depend on the slope of the distribution function. So, if I have a slope of the distribution function like this, f as a function of Vz if I plot, and suppose the distribution function is like this, and this is the point where phase velocity of the wave lies. If the slope of f with Vz is negative, it means slower particles are more than the faster particles. In that case, there is a net transfer of energy. So, in the case when delta f by delta Vz is negative, there are more, that is, there are more slow electrons than the fast ones. Hence, there is a net retardation. Hence, there is net transfer of energy from the wave to the particles. And there is a damping of the wave. And there is damping of the wave. This damping is known as Landau damping. So, it does not really the value of number of particles exactly at omega by k, but in its neighborhood, or it is the slope of the distribution function that should decide whether the wave is damped or amplified. Now, all these effects are taken into consideration or through what we call as the VIasov equation. So, before I go over to VIasov equation, let me formally define a distribution function. Well, let me begin with the definition of a density in three-dimensional space. Density normally we use the symbol n. In general, it is a function of x, y and z, which means the number of electrons per unit space volume is called density. If I multiply n by dx, dy, dz, then this gives me the number of particles, electrons in volume dx, dy and dz. So, if I divide this by dx, dy, dz, you will get the number of particles per unit volume, that is called density. But if I consider unit volume, the electrons that you get, n electrons per unit volume, all the electrons are not moving with the same velocity. Some are moving faster, some are moving slower, some are moving upward, some are going downward, some leftward, some rightwards and so on. So, if different particles are moving with different velocities, if I want to study the interaction of individual particles with waves, then I can subdivide these particles into small velocity ranges. So, what we do? We say that out of these n electrons, let the electrons let me define, or electrons, or the number of electrons rather, the number of electrons in volume dx, dy, dz, obviously total number is n dx, dy, dz, but having their Vx component of velocity in the range Vx, Vx plus dVx, Vy in the range Vy plus Vy plus dVy, and Vz in a small range Vz and Vz plus dVz. So, let me focus not on all the electrons in this volume element, but out of this let me find how many particles are there that have their x component of velocity in the range Vx and Vx plus dVx, y component of velocity in the range Vy and Vy plus slightly large velocity dVy, and similarly Vz. How many particles do I have? Obviously, if the range were not there, then I would expect no particle. So, larger the range, larger the number of particles. So, I expect that this number would be proportional to the products of these velocity ranges. Obviously, it is proportional to dx, dy, dz also as here. So, I write this number of particles, let me call this dn, total number of particles in the volume velocity range. So, this is f dx, dy, dz, dv, let me call capital N rather, not a small n, total number of particles, dvx, dvy, dvz. This is the total number of electrons in the volume element, space volume element dx, dy, dz, and this is called the velocity space volume element dvx, dvy, dvz. So, f is called the distribution function, which is the number of electrons per unit space volume and per unit velocity space volume. So, f, the distribution function, is the number of electrons per unit space volume and per unit velocity space volume. This 6-dimensional space x, y, z, Vx, Vy, Vz space is known as phase space. So, f is known as the distribution function and which can be viewed as a density in thick 6-dimensional phase space is equal to density in 6-dimensional phase space. Just as n was the density in 3-dimensional space, this is the density in 6-dimensional phase space. So, just me write down for comparison, n was the density of particles or electrons in 3-dimensional space, x, y, z space. And just n was a function of 3 variables x, y, z, f will be a function of 6 variables x, y, z, Vx, Vy and Vz. So, let me always keep this comparison in view. N was a function of x, y, z, and f in general is a function of x, y, z, Vx, Vy and Vz. Of course, time dependence is always there, like density in any system besides depending on x, y, z depends on time, f will also depend in general on time. Well, I can write this explicitly. Now, we have, so let me write down a dependence, actually time dependence also here, and let me introduce a time dependence here as well. Now, in case of 3-dimensional density, x, y, z, t dependent density, we have a equation of continuity. And which says that delta n by delta t plus divergence of nv is equal to 0. Nv is called the flux of particles. So, whenever the inflow of particles is different than the outflow of particles in any small volume element or any volume, there will be accumulation of particles in that volume, and this is actually called the equation of continuity. I would like to write down this equation in a slightly different way, which says that delta n by delta t plus divergence of n into, I will write down, actually I can write down this as delta delta x of n Vx, which is dx by dt, I think I should write plus delta delta y of n d y by dt plus delta delta z of n dz by dt, where dz by dt is the z component of velocity of a particle. So, this is the way you could write this is equal to 0. I would like to, I may write this actually dx by dt in a symbolic form as x dot, dy by dt as y dot. So, rather than calling ddt, I could have written this in this way: delta delta t of n plus delta delta x of n x dot plus delta delta y of n y dot plus delta delta z of n z dot is equal to 0. This is the way. I would like to generalize the equation of continuity to 6-dimensional space. So, this del operator I should write down in 6-dimensional space. By similarity, I can write down delta f by delta t plus delta x of n, or rather f x dot, plus delta y of f y dot, plus delta z of f z dot. These are similar terms here, but now 3 additional terms will come because of delta Vx of f Vx dot plus delta Vz f Vz dot plus delta sorry, this should have been Vy. I will write down Vy here. Vy f Vy dot, this should be 0. So, by similarity to equation of continuity, I have written the continuity of equation of continuity for f in 6-dimensional phase space. Now, I would like to remember that x, y, z, Vx, Vy, z, Vz are all independent variables. So, if x dot is Vx, I can take Vx out of this differential sign. This Vy can be taken to be independent of Vy, and so on. And similarly, I can write down about these are after all acceleration. Vx dot is acceleration x component, Vy dot is particle acceleration y component, z component, and so on. So, normally if we are talking of electromagnetic fields in the system, then V dot vector is equal to the electric force if the electron is minus E charge and electric field is E and magnetic force is E V cross B, then this is the electric force, magnetic force divided by mass. This is the acceleration. So, what I should do? I can replace V dot in these equations by this quantity, and these can be written after removing Vx. I can take out of the delta x operator because Vx and x are independent variables. So, when you do this, you get delta f by delta t plus Vx delta x of f plus Vy delta f of delta y plus Vz delta f by delta z. These are the 3 terms having space derivatives. Now, the terms with velocity space derivatives would be, this is plus delta Vx of f multiplied by the x component of acceleration. So, minus E by m is common. So, I can take this minus E upon m outside. Then I am having Ex plus V cross B x component, which would be Vy Bz minus Vz Vy, and similarly other terms. I will not write them explicitly, I will just say that similar terms will be for delta Vy and delta Vz, and this whole sum should be 0. You may note one thing in here, that when delta Vx operates over this inner bracket, it gives you 0 because there is no Vx dependence anywhere. It operates only on f, and hence this inner bracket can be taken out because it has no dependence on Vx. Similarly, if I had written delta Vy term, the term containing E and B, that inner bracket will be independent of Vy, so it can be taken out. That is the beauty here. So, what I am saying is that this acceleration term can be taken out rather than keeping it inside, and this equation takes the following form: delta f by delta t plus these 3 terms can be cast in this form: V dot del F, and these can be written as minus E upon m, taking these force terms outside, which become E plus V cross B dot delta delta V, so I will call the grad V operating over F. This is equal to 0. This is called the Vilasov equation. In which two things, important things have been ignored. One, no collisions have been taken into consideration, and secondly, no ionization or recombination are allowed. If you have to allow for n collisions, then right hand side will not be 0, it will have some number there. Well, the processes of recombination and ionization and collisions are slower processes in plasmas, and consequently in studying the behavior on a shorter time scale than the collision time, etc., you really have to solve this equation with right hand side equal to 0. And this has very rich physics. All resonant wave particle interactions are inherent in this equation. Today I will discuss a very special case when there is no magnetic field in the system, DC or perturbed magnetic field, and there is no DC electric field in the system. So, first of all, I would like to consider equilibrium, that is called field free equilibrium, in which E is 0, B is 0, so this term is 0. Obviously, in the equilibrium, distribution function should not depend on time. So, when this is 0, then this must also be 0. So, for a field free equilibrium, F must be independent of x, y and z. So, that gradient of F is 0. So, now let me consider a special case field free equilibrium. Means E is 0, magnetic field is 0 in the system, and delta F by delta T does not depend on time because we are talking of equilibrium. So, gradient of F must be 0, which implies that F is homogeneous, independent of x, y and z. We call this distribution function as F0. So, F is equal to F0. So, this in general is a function of Vx, Vy, Vz, and many plasmas. This has Maxwellian form. So, I will write down this especially Maxwellian distribution function. It can have different forms also, but for a Maxwellian distribution function, I can write down F0 as, this is N0, the number of electrons per unit volume. This is called density of particles, and then you have m, mass of the electron, upon 2 pi T E, electron temperature in energy units. Boltzmann constant is hidden in temperature, 3/2 exponential minus m V square upon twice T E. This is called the Maxwellian distribution function, and certainly when you substitute this in the Vilasov equation in the absence of any external fields E and B, then this satisfies the Maxwell's equation for any arbitrary value of N0, arbitrary value of TE, and where V square is Vx square plus Vy square plus Vz square. We define a quantity called thermal velocity of electrons as 2 Te upon m under root. Then F0 can be written as N0 into V thermal to the power minus 3, then you have a quantity called pi to the power minus 3 half exponential minus V square upon V thermal square. So, this is a 3-dimensional velocity space distribution function. You can call so called a 6-dimensional phase space distribution function, which is uniform in x, y, z, but which depends on values of Vx, Vy, Vz. I would like to consider now a perturbation. Suppose I perturb the system by some compression or rarefaction of charges somewhere, that gives rise to electric field, and obviously I am expecting that when you have displaced electrons which are uniformly distributed somewhere, suppose you have created more electrons and a depletion of electrons somewhere here, then in such a system you have created electric fields in the system, and those electric fields will then move these electrons from high concentration region to low concentration region, and that will set in oscillations. So, I would like to self consistently study if I have created some initial perturbation in the distribution function and self consistently perturbation in the electric field has been created, then how this perturbation will go with time. So, I am trying to consider a simple one-dimensional situation, that suppose I create a perturbation in electric field which can be expressed as a gradient of a scalar potential phi, which in general is a function of t and z. And I say that my distribution function now is equilibrium distribution function plus some perturbed quantity. So, this accumulation of charges somewhere in space, velocity space or actual space, reduction elsewhere, will give rise to creation of electric fields or electric potentials. I would like to find out the equations governing F1 and the equation governing phi. Well, the equation governing F1 I can deduce from the Vlasov equation, treating F1 to be very small as compared to F0 and perturbed quantities to be very tiny. So, I will consider that the electric field that is produced by the potential, which is minus grad phi, which is equal to in this case minus z cap delta phi by delta z, is a small quantity, very negligibly small, very tiny. F1 is also very tiny. And let us see how it F1 evolves with time. That is my fundamental issue, how the potential evolves with time. Will it damp out or will it grow with time? That is the fundamental problem that Landau examined in 1946. A very pioneering work he carried out. He addressed this issue. So, I would like to substitute this F equal to F0 plus F1 in the Vlasov equation. Let me write down the Vlasov equation. Delta F by delta T plus V dot del F minus E upon M dot delta F by delta V. I will write down V vector, I should have written grad V, equal to 0 because there is no magnetic field, so I did not write that. But I am treating this electric field to be a small perturbation. So, when I put F equal to F0 plus F1, I get the, and recognizing that F0 does not depend on time, it does not depend on position, it depends only on velocity. So, this term will be finite, but other will not be, but product of F1 with E will be ignored. So, I get delta F1 by delta T plus V dot grad F1 is equal to, take this on the right hand side, E upon M Ez, because I am considering my electric field in the z direction, and delta F0 by delta Vz. This is my equation governing F1, but it is in terms of Ez. which I can write down in terms of phi as minus E upon m delta phi by delta z into delta f0 by delta Vz. But what is the equation governing phi? The first equation, Maxwell's equation, is also called the Poisson equation, governs phi in terms of density perturbation. Let me write that equation. The equation is divergence of E multiplied by free space permittivity epsilon 0 is equal to the charge density rho, but this I can write down as electron ion charge density, which was n0 into E. Ions are there in the system with density n0, and I presume that their density is not modified by this perturbation, it is only electron perturbation, minus n0 plus n1, this is the electron density into charge is minus E. So, n0e will cancel out and you will get n1e, but n1e is how much? Number of particles you can get from the distribution function E, which is the perturbed distribution function f1 into dvx, dvy, dvz. It is a triple integral on Vx, Vy, Vz. Ranges are from minus infinity to plus infinity for each. And E, if I write as minus grad phi, this becomes minus epsilon 0 del square phi is this expression. So, it is, and because I am considering only delta delta z variation, I write down this is equal to d2 phi dz square is equal to minus E upon epsilon 0 triple integral f1 dvx, dvy, dvz. So, these are two coupled equations, one governing phi in terms of f1 in the integral form and the other one governing f1 in terms of phi, the perturbed VIasov equation. In order to solve these, Landau carried out Laplace Fourier transform. I will do it in steps. So, consider the Fourier transform first. What I am saying here, that if I have a perturbation f1 which depends on position, then I can write down this space dependence as 1 upon root 2 pi a quantity f1k exponential of I k z dk. Please understand, f1 in general has dependence on time, z, vx, vy and vz. So, as far as z dependence is concerned, I have written as a sum of sin kz terms. This is called Fourier transform, f1k is called Fourier transform of f1, and the values of k goes from minus infinity to plus infinity. And f1k can be written as 1 upon root 2 pi minus infinity to infinity f1 exponential of minus I k z dk, dz, sorry, this is dz. So, this becomes my Fourier transform of perturbed distribution function. Similarly, I can define a Fourier transform of potential phi k as 1 upon root 2 pi minus infinity to infinity phi, which depends on time and z, as I mentioned before, exponential minus I k z dz. So, but my suggestion is that multiply the Poisson equation and the VIasov equation by exponential factor, this minus I k z, and integrate over dz. So, multiply VIasov equation and Poisson's equation, the phi equation, by exponential minus I kz dz and carry out the integration and integrate over dz, integrate over dz, over z rather. When you carry out the integration, what you get essentially is, this is equivalent to, when you do this, then you will say that wherever d2 dz square was there, it is replaced by minus kz square, and wherever delta delta z was there, it is replaced by simply I kz. You can just do it. This integration can be carried out by parts, and this can be done. So, when you do this, the VIasov equation reduces to the following form: delta f1k by delta t plus ik, rather I do not have to put z subscript here, zk is enough. So, ik vz f1k, and then there was this term minus E upon m, this is equal to minus E upon m ik phi k delta f0 by delta vz, and the phi equation becomes the phi equation was, it becomes rather phi k is equal to E upon k square epsilon 0 triple integral f1k dvx dvy dvz. Now, these are two coupled sets still, but one derivative is there in time. So, I would like to carry out the Laplace transform, but I think for today the time is running out. So, we will continue our discussion in the next lecture. What we want to do? We want to carry out the Laplace transform of these quantities and solve for the Laplace transform and carry out the inverse Laplace transform. And when you do this, you have to be careful, and we will follow the Landau prescription. We will do it by contour integration. I think this has very rich physics, and we shall continue in the next lecture. Thank you.